Hello everyone, I'm Oleksii Vasylenko, Galaxy GameDev engineer from Samsung, Ukraine. Today I will briefly talk about what Galaxy GameDev program is, about useful tools to profile your game, and most of the time I'll speak about best practices based on our game's optimization experiences. So, Galaxy GameDev team consists of 5 divisions located in US, UK, Ukraine, China and Korea. It is a team who works with game developers all around the world, providing both on-off-site support for game studios with any kind of problems, such as performance optimization, bug fixing, or any other issues. We have a device loaner program for our partners, and we are actively promoting Vulkan. We believe this is the future of computer graphics and a great way to unlock maximum performance out of the games. So we have many partners. Here are some of them. Our collaboration history starts from 2015, and we have more than 40 successful stories since that time. So why should you use Vulkan? Vulkan is explicit graphics API, meaning that there are much less assumptions on driver side. So work is much closer to hardware, which allows direct control of how work will be executed on hardware. This gives us a number of benefits. First of all, CPU overhead is obviously very small. Also, you can control GPU work coordination and reduce repeated work by doing all of pre-processing upfront. Cross-platforming and multi-threading are another great Vulkan's benefits. And with Vulkan, you can get exactly what you expect to, as there is no more driver guesswork. Another great thing about Vulkan is that it is already supported by both UE4 and Unity engines, so you can get most of features straight out of the box. Next, I want to discuss some tools what we actively use. And these are kind of tools you can use in your development process to get all benefits of using Vulkan in your games. First one is RenderDoc. It is a kind of high-featured frame debugger which works great with Vulkan. It allows you to visually verify exactly what is happening and step through the entire frame call by call. This gives us a lot of control. We can identify engine-side optimizations, such as valid API usage, removing redundant render passes, and updating descriptor sets calls, correct pipeline barriers logic, and also we can easily identify content-side optimizations. For example, we can check that large textures are not used for small particles, we are using reasonable render target format, or draw calls are sorted in proper order to avoid overdraws. We can even modify shaders and immediately get the visual result of the change on screen and much more. The other tool we use, which can be used only for ARMS hardware, it is kind of static counter-based profiler called Streamline. This gives really high frequency breakdown of exactly what hardware is doing. You get information about hardware activity, detailed CPU utilization by core, memory bandwidth, and so on. Also, we can zoom in high resolution of the data to check very specific bottlenecks like bubbles between vertex and fragment activities, which is almost impossible to find in any other way. Having these tools on board, we can easily make game analysis. So let's jump in performance optimizations. In Vulkan, you need to use DescriptorSet object to pass resources to shaders. However, updating descriptor sets for each draw call is very expensive on mobile devices. So make sure to optimize your implementation so it's more efficient than simple updating each draw. With such logic, update descriptor sets can take longer times than draw call itself. We really face such cases in our practice. It is much better to implement DescriptorSet Cache and reuse already updated descriptor sets, with efficient implementation, there will be only few updates per frame in average. This helps to significantly reduce CPU usage, especially on mobile platforms. But do not use image and buffer handles as a key for caching. According to Vulkan spec, different types of objects may share same handles. But what is even more important is that handles may be reused after object's destruction. So if you use handles for caching, you need to be very careful and remove all dead entries. And this dead object tracking logic may have significant CPU overhead and make the cache inefficient. It is much safer to assign unique ID for each created object instead, and much easier. In Vulkan, all work is recorded to common buffers, which are later submitted to the Vulkan command queue. When queueSubmit is called, submitted work is decomposed into units of work called atoms. These atoms are then submitted to the kernel queue, and this queue has a limited size. A requirement of the Mali driver is that an atom's execution dependencies need to have been completed before that atom itself is submitted. Moving on from this, a condition imposed by the driver is that the queue present will only return once all associated atoms have at least been submitted to the kernel queue, as this is a guarantee that the work will execute on the GPU. In Vulkan, given it is common to submit all work in one go, blocking happens when queuePresent is called immediately after queueSubmit. It will likely block as common workflow generates more than the allowed amount of atoms per queueSubmit. This is not an issue in GLES due to the driver submitting work more progressively. So we can do the same in Vulkan on the application side. Simply submit your comments after each header in the pass or after a few lightweights. Do not collect all work for GPU till the end of the frame. If your application frame buffer's orientation doesn't match the display's native orientation, Android needs to apply an additional rotation every time a rendered frame appears on screen. This additional rotation might incur a performance cost, depending on the device's hardware capabilities. With enabled pre-transform, image composition time might be significantly reduced. This might not only improve performance of your game, but also protect it from frame drops and frame stuttering. On the latest Adreno devices, there is now a Vulkan extension for correctly handling pre-transform on swap chain images. The extension handles the internal conversion for coordinates of swap chain image, like viewport, scissor values, and so on. In case of Mali, you should care about all this stuff by yourself, as well as changing projection metrics, updating screen texture coordinates, which obviously makes things much more complicated, especially for game engines, because it is quite hard to manage rotation impact in general way, as some shaders may not use the projection metrics, or shaders may depend on current pixel position, or by any other reason. So we really hope to have a similar extension for Mali devices. Till that time, extra responsibility is falling on the developer's shoulders, but it is definitely worth it to apply pre-transform in your game. Subpasses. During normal rendering, it is not possible for a fragment shader to access the attachments to which it is currently rendering. GPUs have optimized hardware for writing to the attachments and accessing the attachment interferes with this. However, some common rendering techniques rely on being able to access the result of previous rendering during shading. For a tile-based renderer, the results of previous rendering can efficiently stay on chip if subsequent rendering operations are at the same resolution, and if only the data in the pixel currently being rendered is needed. In order to help optimize such techniques like deferred shading on tile-based renderers, Vulkan splits the rendering operations of the render path into subpasses. All subpasses in render pass share the same resolution and tile arrangement, and as a result, they can access results of previous subpass. In Vulkan, a render pass consists of one or more subpasses. For simple rendering operations, there may be only a single subpass in the render pass. First, what comes to mind thinking about when to use multiple subpasses is deferred shading. Unfortunately, still in our practice, there were only few cases when deferred shading was used in real games. Anyway, there is another simple example when multiple subpasses can be used in forward rendering case and give performance benefits. In most cases, you need to use depth buffer filled with opaque objects data for translucency pass. In such situation, normally you will have two render passes. You will render opaque objects in the first one, then at the end of the render pass store both color and image and depth images to system memory and load them back when starting the second render pass with translucent objects. And this will take much memory bandwidth. With multiple subpasses, you can keep all necessary data on chip, significantly reducing memory bandwidth. In such case, there is single render pass with two subpasses. In the second subpass, depth is used as input attachment from the first one. Also, there is no need to load and store color attachment anymore. All data stays on chip. Even such simple optimization can give significant performance boost. Here you can see results of depth fetching by using multiple subpasses, the top row, in comparison with regular logic. Mali GPUs include the ability to perform LZ testing. It improves performance by skipping execution of fragment shader for fragments, which will be discarded after depth testing. The Mali GPU typically executes the LZ algorithm on most content, but there are cases where it is not executed. While optimizing games, we often face when discards are used in shaders, even they might be avoided. Discard usage will stop LZ algorithm execution to preserve correctness. As depth buffer will be already overwritten with wrong value, even fragment would be discarded. And that will cause performance degradation, GPU load increase, as there will be much more over the wrong fragments. Among discards, you should avoid doing following things without need. Write to depth buffer, use alpha to coverage, use depth bias, as all of this will stop LZ execution. Vulkan is explicit API, meaning also that it should be used very carefully and wisely. You should use exactly what you need to. All redundant logic should be avoided. For example, ARM GPUs have AFBC technology on board. ARM frame buffer compression is a real-time lossless compression algorithm. It is applied to frame buffers that are to be written to the GPU. This technology can offer bandwidth reduction of up to 50%, which is huge. AFBC is functionally transparent to the application and will be automatically applied on a per image basis. But in Vulkan, in some cases, it might be disabled by app developers, even they don't want to do so. For example, still these days, compute shaders are not very popular on mobile. So it's a quite rare case when the frame buffer's image is used to be written to in compute shader. Therefore, there is no need to add storage bit flag when create such image, as applying this flag will disable AFBC. But many times we faced when app developers put all flags not thinking that it could reduce overall game performance. This is just one simple example, but there are many other situations like this. Also, quite often developers set redundant stages to pipeline barriers, put extra flags when creating common buffer pools, and many other things. So with Vulkan, it is very important to always use exactly what you need to, not less, neither more. Pipeline is a complex object that describes how primitives should be rendered. However, creating a pipeline object is very expensive. So you need to use pipeline cache and create pipelines during loading time to improve performance and avoid hitching in runtime. Even so, creating a lot of unique pipelines for the first time with empty cache takes a long time. ARM chips use big. LITTLE technology, coupling relatively battery-saving and slower cores with relatively powerful and power-hungry ones. Taking this into account, to speed up pipeline creation, the task should be moved to high-performance cores. For example, in case of Fortnite, using all cores instead of only little cores helps us to reduce loading time for more than twice. So always make sure costly operations can be done in the right place. As it was mentioned at the beginning, there is no more driver guesswork with Vulkan. Well, this is almost true. Still, we face few driver-specific issues in our practice. For example, Mali GPUs has transaction elimination feature. It's a great bandwidth-saving feature, and when performing transaction elimination, the GPU compares the current frame buffer with previously rendered frame and performs a partial update only to the particular parts of it that have been modified, thus significantly reducing the amount of data that need to be transmitted per frame to external memory. Transaction elimination can be used by every application for all frame buffer formats supported by the GPU, irrespective of the frame buffer precision requirements, and is highly effective even on first-person shooter games and video. It is really cool and important feature. It's also to have it on Mali GPUs. But with some driver versions, we face the following issue. If clear attachment without something rendering to it, image clearing will be skipped due to transaction elimination, and the image remains dirty. This problem could be solved by switching current image layout of image you want to clear to general and back to original one. Such round trip will drop existing cache and force to update the entire image. Android ecosystem is quite complicated. There are so many different devices with different hardware and different feature sets. Even devices look similar, they easily might have different hardware. This is one more reason why Vulkan explicitness is so important. Samsung flagship devices are manufactured with two different chipsets, ARM and Qualcomm. Usually, our partners test their games with both, and sometimes they are really wondering why performance is so different. For example, there was a game with a quality level that set MSA value to 2 samples. With such quality settings, devices based on Qualcomm chipset showed better results. The reason was that Mali GPUs don't support 2-color samples. Therefore, there was fallback to 4 samples, which is obviously much heavier GPU work. So, before doing anything with Vulkan, always consider device limits first. Also, there might be some driver-side limitations which you could not check even with device limits. For example, some Mali drivers have a limitation on the amount of available shader memory. We faced games like Fortnite that creates a very large number of pipelines, far exceeding these limits. And we implemented a less recently used tracker for Vulkan pipelines to manage this issue. Using a heuristic, we assign a predicted device shader memory size to each pipeline and check whether creating a new Vulkan pipeline is expected to exceed the memory limit. If we predict that the limit would be exceeded, we delete the least recently used Vulkan pipeline. This solution obviously helps us. There were no more crashes related to this driver limitation. But it requires the creation and destruction of Vulkan pipelines during gameplay, and therefore has a negative impact on performance. Without this fix, it is unfortunately impossible to use a huge variety of shaders on some Mali devices. That's all from me. I believe this information will be useful in your ongoing and future projects. The last thing I want to suggest is start using Vulkan today. Thanks for watching, take care, and enjoy ARM DevSummit.